Oh, hi. Welcome everyone to our virtual lecture. It's now 10:50, actually 10:51. And just gonna get started with our lecture. Today we will start from where we stopped on Tuesday. We started chapter 1. We went as far as section 1.4, which is on energy. I want to get started with section 1.4. If you have no question regarding the previous uh, section 1.1, 1.2, and 1.3, we will just get started with section 1.4, which is on energy. I know the previous section, it was kind of like review from the previous intro to chemistry, or if you are taking this course, it's just like an overview on how to classify matter as pure substances, mixtures, compounds, elements. You know, we went through solid state, liquid state, and all those other properties we talked about. Please review and continue working on the homework assignment, which I did post on my lab on mastering chemistry. Without wasting my time, let's look at energy. I know this time here, it's not new to you. Energy is simply defined as the ability or the capacity to do work or the heat transfer. We're going to talk about heat in details in chapter 5, but for now, you should be able to define what energy is. Energy is the ability to do work or capacity to do work or heat transfer. And what is work? Work is simply the transfer of energy transferred when uh, force is exerted on an object. You may be asked to find the work, you know, from this equation. Work equals to force times distance. You may see this, or you may have seen this equation in physics, or simply force times distance gives you the equation for finding work. So those are the two terms you should be able to define. In relation to that, heat, no, we say energy is heat transfer. And what is heat? It is the energy used or caused to the temperature of an object to increase. It's the amount of energy used to raise the temperature of an object. You know, it can be transferred from cold to hot object. Simply force is a push or a pull. You know, those are the terms used to in relation to energy, and energy is simply the ability to do work. Those four terms you should be able to state in an exam. All right. Now, looking at the fundamental forms of energy, there are about six types of energy, but as far as this course is concerned, there are two forms you will see in chemistry, and these are the potential energy. All right, there is the potential energy. Simply, sometimes it is abbreviated as P E for potential energy and kinetic energy. These are the two types of energy you should understand. You should be able to differentiate between the two, abbreviated as PE and KE for kinetic energy. Kinetic energy. Kinetic energy is simply the energy in motion. It is the energy possessed by uh, by moving object. We can have our kinetic energy here is a half times mv square, where v stand for the velocity. You see here velocity and mass. Commonly, you will be asked to calculate the kinetic energy of an object. And this is the equation you will need, Ke for kinetic energy. Well, it is easier to remember, to memorize, but what might get you is this term right here. What I've circled is where there is a catch. You should know what are the units, all right, of mass. What are the units of V or speed? This mass should be in kg, which means kilogram, all right? If mass is in pounds, if mass is in ounces, if mass is in gram, you should always convert to kilogram. And velocity or speed, this should be in meters per second. So if an object is moving at a speed or velocity in miles per hour, you should be able to convert the miles to meters. If it is in kilometers, convert to meters, so that when you square this, you'll end up with the units being kg meter square, all right, per velocity square, which is related to now the SI units for energy. I know you are familiar with joule. We're going to talk about this. It is the same as kg meter square per second square. So this is what you need to remember as far as calculating the kinetic energy of an object. Kinetic energy of an object. We have the other form of energy, no, not that. Which is potential energy. Potential energy is simply the energy possessed by object by virtue of position or chemical or composition, all right? It is stored energy. Potential energy is stored energy. You can call this simply the stored energy. Is the energy stored by an object. This is R right here. Or the energy possessed by a substance by virtue of its composition. Gasoline has energy, all right? If the chemical bonds are broken, energy is given off. The food we consume has energy, all right? And those are other forms of energy. These are the two forms of energy you should be able to explain in your own word. I want to look at one example on the calculation of kinetic energy. But before we do that, this is what I was explaining earlier on in regards to the units of energy, which is joules. This is the SI units for expressing energy. Joule, J-O-U-L-E, simply abbreviated as J. And it is related to now, you know, the units you'll end up with when you multiply the mass of an object, right here, mass, in kilogram times velocity square. V square means, you know, m raised to 2, s raised to 2 is because of the velocity. Velocity is in meters per square. If we square this, we're gonna square everything on that side to give us meter per square, which means if you end up with the units, you can change these to joules. Understand this, you may not be given in an exam, but you are expected to know that 1 joule equals to kilogram times meter square per second. It's the same thing as this, K meter square, and then I put second there. It's the same thing, right? It doesn't change much. There are two, all right, there are two units of energy which I want to distinguish. And from where you are, you may not be in a position to even really capture what is going on. If you look at the if you look at the calorie here and the calorie here, the difference is the uppercase and lowercase. This is lowercase and this is the uppercase. Nutritionists use this uppercase calorie to mean the amount of energy consumed. So when you see a can of soda with this value, maybe 170 calories like that, essentially what that means is it is 170 thousand, all right, lowercase calories, because 1 calorie uppercase is the same as 1,000 calories. So next time, all right, next time you you see the labels on any food with the caloric content, understand that they are using the uppercase. This is what the nutritionists use. And the lowercase calorie is the same as 1,000. You can change that. Quite often I see questions saying that what is the energy in joules? 1 joule or 1 calorie lowercase is 1,000. 1 calorie lowercase is the same as 4.184 joules. These are the conversion factors. I mean, equivalent statement you need to remember down the line when you are asked to calculate either energy in joules or energy in calories or kilocalories. We're gonna talk about that later on. We're gonna talk about that later on. Let me see if we have somebody joining us. All right, thank you. So that is what you need to remember as far as the kinetic energy. Here is an example, all right. A baseball weighs 5.13 ounces. What is the kinetic energy in joules of this ball when it is thrown by a major pitcher, a major league pitcher at what? At 95.0 miles per hour. The speed there is in miles per hour. You are expected to convert the speed from miles, all right, from miles per hour. Okay, how are we going to change miles per hour to meters per second? You have to know that in 1 mile, all right, 1 mile equals to 1.609 kilometer, which means 1 mile equals to 1.1, not 1. If I change that to meters, 1 kilometer equals to 1,000 meters. This is kilometer. So multiply that by 1,000, you end up with 109 meters, 109 meters. So if I change the miles, which is 95.0, all right, 95.0, 95.0, somebody's, should we have this conversion memorized? I will say that you should know, Caroline, you should know, or you should be able to find, say if you are taking a homework, how do I do that? In the exam, you will be given those, all right? If need be, I'll look at the questions in beforehand. If need be, I should say you should know this in the study guide, but for your case, know how to do that. Right now, I haven't looked at the exam to tell you that you should know this. I'll indicate in my study guide if you need to know this, that how many calories are in 1 uppercase calorie and how many joules, but you should be able to know how many, because when you do the homework, it's not gonna tell you do this. For example, All right, for example, right here in this example on the screen, you are not given, let me just go back to, you are not given these conversion factors I do have here. How do I know that? It's just by knowing, but if I'm sitting where you are, I just have to use the text, to use, any other resource to find out how do I change from miles to hour with an understanding that this is the objective. You see this? This is where I want to go. And that is what I'm trying to do right now here. Miles, right there. I want to change, this is 1 mile, to meters. This is 1609 meters. So you're gonna multiply that pi 1,000. See first before I respond to that. 95.0 times 1609. All right, I have 152,855. So this is 152,855. This is in meters now. This is meters. Somebody is asking, I don't know if you already addressed this, but when is the fast quiz? Normally what I intend to do with the fast quiz is when I'm done with the chapter, for example, we'll be done with chapter 1 today, and then I'll give you chapter 1 quiz and give you time. Somebody, can you move the screen down? This one, I don't know if this is the screen you're talking about, or this one. Is this the screen? Let me see. Are we okay, Anthony? Yes, thank you. All right. Oh yeah, I guess it's, let me see if I can minimize this like that. All right, yes, this is what I was talking about in terms of changing to from miles to what? To meters. I wasn't, say for example, if in the exam and I may give you at the end that this is what you need, like, at the end of each problem for save you time, that 1 kilometer equals to, I may give you this at the end. And then you take it from there. Some of them you already know, like 1 kilometer equals to 1,000 meters. So if I change that 152.85 per hour, in 1 hour, we have 60 minutes. And in 1 minute, we have 60 seconds. So I can divide this by 3,600 to change to what? To change to seconds. So if I divide that by 2, that will give me my speed in what? Speed in meters per second, and I have here 4.459 and this is meters per second. I've changed this speed you see here from miles per hour to meters per second. Yes, Crystal, the number below 1, that is because per hour, it was per hour. If you see this per hour, 1 hour, 1 hour equals to 60. 1 hour equals to 60 what? 60 seconds. And 1 minute equals to 60, no, 1 hour equals to what? 60 minutes. I meant to say this is 60 minutes, and this is 60 seconds. So if you say 1 hour equals to 3600 seconds, that's the number where it came from, divided by, because per, if you look at here, it means per means you divide. So in that way, I can have 15, all right, 15, 152,855, this was meters per 36,000 right there. Because of what? Because of this per hour. That's why I'm dividing it. It say per hour. That means you divide. And that is where I get, this is where I got this number right here. That's where I got that number right there. To change this to what? To change that to meters per second, because what we are trying to do is apply this equation right here, which is kinetic energy equals to a half mv squared. We got to find this term first, meters per second, and then you're gonna square that. What we haven't changed is mass. How do we know what is the mass of the base pole? It is given there. The mass of the base pole is 5.13. Are we okay, Crystal? All right, thank you. All right, 1 mile, yeah, you get that. 1 mile equals, it should be 1 mile. Let's see, did I miss that? Let's see how I did that. 1 mile. 1 mile, it should be Andrew, should be 1 mile under one, no, it's because you are changing mile. You are changing miles to meter. So you want to, look at this. You want to cancel mile and mile here, unit reconciliation. Because of this miles right here. You see this mile? I want to get mile and the meter at the top, not underneath. Not underneath, take care of that. So that should be clear. We're gonna look at the dimensional analysis. How many ounces or how many grams are in 1 ounce? Somebody check. Let me give you an idea of how you can use the resources before you can. Somebody Google out 1 ounce equals to how many grams. You can Google out, you know. If you're doing homework, you can do that, it's allowed. So long as you know what you do, but not in the exam. How many? Somebody just check for us using the, use your phone, Google out how many ounces or how many grams are in 1 ounce. Because, all right, yes. Thank you. So what we will do now is change this 5.13 ounces. This is how you, if you don't know how to set it up, you want to cancel ounces right there. You are looking for what? You're looking for grams. You say 0.03 or 28, that is grams, okay. So 1 ounce, maybe I need to, you can use anyone. So I'm gonna change this to something else right here. Somebody say 1 ounce equals to 28 point what, 28 point, this is point 35 grams. But if I cancel this and that, I'll remain with what? With grams. I want to get rid of grams and remain with kg. So this will be 1,000 grams is in 1 kg. We want to cancel grams and cancel with grams so that we end up with our mass in kg. Divide or multiply everything at the top, 5.13, all right, times 28.35. All right, divided by 1,000, divided by 1,000. So that is 0. What? 0.14. 5. Yeah, you can say 5. This is kg. This is kilogram. This is kilogram. It's okay, Ali. So we're gonna learn out of mistakes, so you know how to set up next time. So what I have here now is the mass in what? Mass in kg. Kinetic energy is equals to now a half mv squared. We know mass is in kilogram, So a half times 0.145 times 42, it was 42.4597, 42.4597. So that 42.95, 95, 45, that 97, 45, 97. This is 97 here. So this is 9, 7. And remember, this is a square. That is a square. You square that because it is velocity square. Velocity square. All right. So you can square that fast. You could start with 42 point. This is 45. This is 45 here. There is 45. 45, 97 raised to 2, that is square, times 0.145 divided by 2, that is half. I get 130, and this is 130.7 0. This is now kg meter square per second square, because we were squaring the velocity. We are squaring the velocity. This is the same as, you may see multiple choice that instead of that, it might give you only one, 130.7 joules or 0 joules, joules like that, or joules. And that is what I expect you to do. You know, it's a compound. It may seem easy when you look at the equation. You may be given equation, but the catch is right here. How do I change the units? How do I know this? They expect you that, you know, you took introduction to chemistry, and you should be able to bring over, all right? Bring over whatever you learned before, and then apply in calculation. With what we just talked about, you may be asked to find in kilocalories, all right, or calories, all right. You can be asked to calculate in calories. Somebody say, can you scroll back to the previous slide? Let me go back then. This one right here. Christian, you have a question over here? You say go to the previous slide. Oh, calculation page, okay. I'm gonna go to the calculation page right here. Let me see, maybe did I make a mistake? Right there. I think this is right here. This was our velocity, and I plug it in this equation, half mv squared times 0.145. This is the mass right here, and this is the velocity. I square that because of half mv squared. All right, good. Let's move on. So I was saying that it might be also tagged to this. You'll see at the end of the chapter problems, you may be asked in kilocalories or you know, or calories. For example, here I can change to calories by doing this. I can change to calorie. This is this is lowercase calorie, 4.184. All right, 84 joules, and joules and joules will cancel, and then I end up with lowercase calories, and 1 calorie equals to, you know, 1,000 lower calories, just going around for that. So that is a typical question on the kinetic energy. No one will ask you to calculate the potential energy, but remember to do practice on how to calculate or determine the kinetic energy of an object. Key thing to remember is always mass has to be in kilogram. The only thing is, if I change this to pounds, how will I change pounds to kilogram? If you are given in other units, how will you change that to kilogram? Other units here could be in kilometers per hour, you know. You should be able to change that to meters per second, meters per second. That's the only thing. If I can remember how to change this, remember the units. Determine the units here, determine how you will make this conversion on kinetic energy, before we look at the concept of significant figures, any question on kinetic energy? Any question on kinetic energy? All right, let's move on to the numbers and calculation. Before we look at the significant figures, there are two types of numbers you'll encounter in chemistry. We call these exact and inexact. All right, numbers, exact or inexact, and we use numbers to quantify, especially when we talk about measurement. We should have a number and a unit attached to it. Otherwise, in chemistry and in any science field, a measurement with no units attached to it is just meaningless. It will just be a meaningless number. So whatever you record your measurement in the lab data sheet or whatever you're recording, it should have a unit attached to it. Now, if we don't have units, we will not know what you're talking about. For example, the distance from here to Miami could be 365 miles. If you don't indicate miles, somebody might say, is it kilometers, is it meters, is it yards, and so forth. We should always include units in measurement, right? At some point, we will do calculation, for example, density. And when you do calculation, you end up with more than what you need. You will have to look at how you round off those to the correct number of significant figures. It is important to know that all measurement in the lab, or generally all measurements are not exact. In other words, there are some degree of uncertainty that you are not certain. We'll see how the uncertainty comes in with respect to significant figures. Significant means important. I've heard people say that, who is your utter significant? That means somebody who's important to you. You have heard about that before. And the most important thing is, how do we count the significant digits? That's gonna be the last thing. But for that, measurement. In chemistry, there are three types of units of measurement used. I'm gonna draw a parallel, all right, so that you know what are the three units of measurement. I don't know if you can draw a parallel between the three units. We have what we call the SI, which you look at, you see from the screen, that stand for System International. It was derived by scientists, where international means, worldwide. How did we end up with these SI units? Before, people used to do business in a way it could make sense. For example, somebody say, how tall are you? Some people might say 5'10" or 6'1". That means 6 feet, 1 inch. How did we end up with a feet? We know feet or a foot, your foot, your feet, right? Back in the day when they were using, a unit of measurement for measuring the length, for example, the length of my stylus here, they used to base on the king's foot. Like if I'm a king, they were gonna use my foot as a standard of measurement. But you can imagine that, a skinny king, a huge king with a large foot, they were inconsistency. And that is why they devised a uniform system we call System International, or SI. We have what we call the metric right here, which we use heavily in the lab. I don't know why, When we come to lab, we use the metric, but when we go home in the real world where we live, we use what we call English, all right, English system of measurement. There are 3 systems. And I'm going to show you using some physical quantities measured here. If, say, for example, you are measuring length, so that you know the difference, we use this kilometer. We use here meter abbreviated as M, and here you see several, you will see several units. For example, yards, all right? 9-yard penalty. You see when they're using the football, they're talking about the yards, 10-yard or whatever, they say they use yards. Here we have miles. We just talked about miles, and whatever you're just driving home, speedometer reads in miles per, per hour. What you didn't know is that those are English unit of measurement. I can give you another example here, wherever we use a volume, all right? When we measure volume, we talk about meter cubic. They use here meter cubic. But here, they use liter. And here, they might have fluid ounces, fluid ounces. All right, we talk about fluid ounces. All right, we talk about gallons. Whenever you go cast your car, the pump dispense gasoline in gallons. That's what I was saying, that back home we use English, and in school we use the metric, like in the procedure for the lab. How many milliliters do you need to measure out? Oh, you need 5 ml of reagent A, or 10 ml of reagent B. We don't talk about the gallons, like, oh, can you get 0.88 gallons from the fume hood? No, we use the metric system. How many centimeters is your lab manual? We use the metric. We don't say how many yards is your lab manual. Here is another example of say mass. I can give you mass. Here we use kilogram, but here we use grams as the base unit, and mass here it could be pounds. All right, pounds. How much do you weigh? I weigh XYZ pounds. I need to barbecue, but I don't know how many people will turn up for my weekend barbecue or whatever. You talk about the steak in pounds, chicken pounds. So please, when you make your own notes, understand that there are 3 basics, so that when you see a unit of measurement somewhere, is it based on those 3? So there is the System International here, which is use different sets of quantities. I've given you examples of physical quantity for length, abbreviated meter, mass for kilogram, this one, I made a mistake. This SI for length, they use meter too. This one is meter, in that meter. Mass, kilogram, temperature, Kelvin, time, second. These are the 7 on table 1.3. Those are the 7 pace unit. What is meant by pace? That means where you are starting with. Where you are starting with. We will come back why we use this guy right here. This middle one right here, we use this for a reason. We're gonna come back in a moment, all right? The System International, do some system use the same base unit? Yes, there's sometimes it's the same. For example, meter and meter is the same thing. We can have, like time, second, and second in metric. To some system use the same base unit. Yes, some units gonna be the same. For example, second here is second for time. For SI, it is second. In metric, it's also second, so it's the same. Some of them, they are the same. But what I want you to pay attention is the metric. We're gonna focus on metric. Wherever, or you may have a feeling that in the lab we use the metric. And by the way, we used to use metric English of measurement in the outside world when we go home. Like on the road, we used to drive in kilometers per hour. The gasoline pump used to dispense gasoline in liters, not gallons. But one president, I don't remember his name, used to executive power to change to English. That's a different story. You may want to check. Who changed, the unit of measurement from metric to English? Somebody changed that. So this is the metric now. So having talked about the SI, you should know that metrics is another system of measurement with the pace unit for mass, that is gram, length meter, second, and temperature is Celsius, Kelvin. Sometimes they use that. So when you see on the diagram here, fluid ounce, 12 fluid ounce, that is English. But 355 ml, that is the metric. That is the metric. So that is what it is. We'll come back later on to the unit of measurement used by chemists, the mole, which indicates the amount of what? Amount of particles, amount of substance. It's a unit of expressing number of items, the mole. Just to give you a heads up, 1 mole, MOEL, abbreviated MOL, like that, equals to Avogadro number of things, Avogadro number of things. Anything you can think of, to give you a heads up. It's a unit of expressing number of items. We will come back to that later on. So these are the pace unit. Why do we use, all right, why do we use the metric system in labs, or why is it, what is the preference of, why do metric system preferred over the English? It's because of what you see here, prefixes. Prefixes are used to either increase or decrease the pace unit. The prefixes cannot be used in English, all right? We cannot use prefixes right here in the SI unit. We cannot use prefixes in the English. We use prefixes in what I've circled there, the metric system. That's the advantage of why we use this. We can express a very large value or a very small value conveniently using the prefixes. For example, mil. What does mil means? That means we have reduced the base unit. What you see here is we use prefixes to increase. To increase, we use prefixes to increase, or decrease what? Decrease the metric, let me be specific, metric, pace unit of measurement, all right. That is the purpose of the prefixes you see. Don't just say, oh, let me memorize what it is. They are used to increase or decrease the pace unit. For example, if I say, my storage, my phone is, 128 gigabytes. Some of you may know, wherever you shop for your phone. I was trying to upgrade my phone. I say, should I go for the iPhone SE for second edition? They are saying they're gonna release, or should I go with Samsung? But I'm looking at the storage. This one I'll get 128. When they say 128 or 256 GB, that means gigabytes. A byte is a unit of storage in computers. So when we say giga, that means you are increasing the base unit by this 1 times 10 raised to what? Raised to 9 byte. I don't know if that is what it is, but you increase 1 times 10. times 10 raised. So kilogram, when I say kg, 1 kg equals to 1,000 gram. Remember, base unit for mass, this is increasing by 1 times 10 raised to 3 what? The base unit. You should know, all right, in this slide, table 1.4, please memorize the names of the prefixes. Peta means you have raised the base unit by this value, 1 times 10 raised to 15. These are just examples. Tera means you have increased by 1 times 10 raised to 12, the base unit. So it could be terabytes. That means you have increased the storage capacity. Teragram, that means you have increased by times 10 to 12. Gigabytes times 10 raised to positive 9. Mega, all right, you have heard about mega and then hertz. You'll see that. That means you have the frequency times 10 raised to what? Positive 6. Kilo, deci, centi, milli, micro, all right. Differentiate between milli and micro. Micro is used the Greek term or the Greek symbol. And then there is the nano times 10 to negative 9 pico femto. So please remember those prefixes. Here are 2 examples. Here are 2 examples to show you how you can be tested. Somebody is asking a question, Andrew, how come microliter is raised to B? There is a footnote. It's just a footnote. Let me go back. It's because of the footnote. This footnote right here, Greek mu pronounced mu. This is based on this, the few micro, mu, we call it mu. This is the footnote here. We pronounce it for pronunciation. If you also look at where we have raised it, A here, there is A right here. What as watts? In relation to energy, they are explaining to you what a watt is. 1 watt equals to the same joules per second, all right? That's what it is. That's what's going on with the abbreviation. So back to where we are, how can you be tested? What do you expect? Question from the prefixes. Either what exponential notation do the following abbreviation represent? Deci, I believe A, all right, 1 times 10 raised to negative 1. Decigram, you know. B, this is 1 times 10 raised to 6. And C, picometer, all right, times 10 raised to what? C, 1 times 10 raised to negative 12. Is it negative 12? Yeah, negative 12. From this one, that is where they are asking you, pico, right there. So you have to remember the name. Sometimes you may be given this and what does it mean? Or this one, what does it mean? Nano means what? Or if given this, how does it or increase by what value? By what value? So that's what I'll do for question 1. For question 2, use the appropriate metric prefixes to write the following measurement without the exponent, all right? Is there a chart in Canvas with all these prefixes? I'm gonna put it for you, all right? I'm gonna put it for you, the complete table on that, prefixes. Anthony, what did you say about P? Someone had asked a question about this. This is where the P came from. Somebody was asking, Anthony, somebody was asking, why is this guy raised to P as in poi right here? Like nothing here is raised to anything. Is there anything special with this micro thing? And then I pointed out that it has to do with the footnote, like footnote. So if I look at this also, look at where A is here. They are just trying to explain what watts is with respect to joules. So that is where the P came in. And that is what it is. It has nothing to do with the numerical file. It's just as simple here. Like somebody might say, what is micro here? What is micro? That is what it is. I think it is, Jennifer is saying, I think it is mega. Somebody is saying mega? No, let's see. Mega is right here. M is mega, M. All right. But P right here is what we are talking about. Sierra, thank you. All right, so here are question 2. This is 4 point, I'll write this as 4.7 micro. You'll say this microgram. Why am I, you see how I'm changing this? It's because of this times 10 raised to 6 stand for what? Stand for micro. Times 10 raised to 12, that will be 1.85 times, not times, but this, we don't need that. We don't need this. This is pico what? Picometer. So it's just gonna be picometer like that. Picometer times 10 raised to 12. That's what you expect to be tested on the table. I'll post on Canvas that table. It is in the text. If you want to, if you have the text, it is in the text on page. Let me see where the page is for that. Now that you have said that, the prefixes for measurement, you should have it on page. It is on page 18. If you look at page 18, all right, page 18, in the text, you'll see table 4. And in any case, if you can access the e-text, you can also check on the on that. But to save time, I'll have a table on Canvas with all those prefixes. Let's see. We are done with those prefixes. Let's real quick look at the mass measurement and the length. Still on metric system. You should know the base unit for measuring mass, and of course, mass is defined as the amount of matter in an object. Mass is the amount of matter in an object. Don't confuse the difference between weight and mass. Weight is the gravitational force. This is different from, you see, weight like that. Should use this weight. This is a gravitational force acting on an object. All right. And it changes from location to location. It can change from, you know, the weight, your weight on moon is different from the weight on Earth, okay? Your weight will change, but the amount of matter will not change. SI unit for mass, SI unit we use is kilogram for that. We're gonna have length, meter is the base unit for that, and volume for SI we use meter cubic. This is the SI unit for mass, SI unit for volume, meter cubic. We use the liter. This is for liter is the base unit for measuring volume in metric. This is for SI. Remember metric, meter cubic. Liter is the metric system. I've seen question testing students whether they can differentiate between metric and system international, that in SI In SI, what is the base unit for measuring volume? What is the base unit for measuring length and so forth? Draw the parallel between the two. So whenever we use liter, that is the metric, and we use meter cubic for volume in SI. I won't go in details on how this was derived. Please read more on volume. These are just few lab equipment you will encounter. Probably you have used before in the lab. These are common volumetric glassware you will use to measure the volume: graduated cylinder, syringes, purette, pipette, all right, and volumetric. We have other glassware such as beakers. All these are used to measure the volume of a reagent. Before we look at the significant figures, any question before I get started with the temperature? Any question first? Any question? Good. What is temperature compared to heat? Temperature is simply defined as the average kinetic energy of particles of an object. It's a measure of the average kinetic energy. Simply energy is, simply temperature is the average kinetic energy. It's a measure of average kinetic energy of particles of matter. Whereas heat indicates only the heat transfer from cold to, from hot to cold object. There are three units which I want you to know as far as temperature is concerned. These are the three units of measuring temperature. There is Kelvin, K for Kelvin, the unit for that, and then there is degrees. This is degrees Fahrenheit, and degrees units for measuring temperature. Temperature, we can use degrees Fahrenheit, degrees Celsius. We don't have the degree symbol for Kelvin scale, Kelvin scale. All these three scales right here, temperature can be expressed in any of those units. And to change this, I want you to look at how do we change from one system to another. I know you know this, how to change degrees Celsius to Kelvin, all right? Kelvin is given by degrees Celsius plus 273.15. Sometimes they don't have 1.5, it's the same thing. Sometimes they only have 273, not 273.15. Alternatively, degrees Celsius given Kelvin, you subtract 273.15. It's just algebra. So if I want to change from degrees, from Kelvin to degrees Celsius, this is the equation. If I want to change degrees Celsius to Kelvin, this is the equation right here. Now, this equation here, to change from degrees Celsius to Fahrenheit, you have to know how do I change from degrees Fahrenheit to degrees Celsius, degrees Fahrenheit to degrees Celsius. For this, this is the equation. From degrees Fahrenheit, you'll change the equation by using 1.8, or sometimes we use 9.5 over 9 or 9 over 5. Here, 9 over 5 is the same as 1.8 degrees Celsius to degrees Fahrenheit, like that. That means degrees Fahrenheit equals to 1.8 times degrees Celsius. Please use parentheses. I've seen a student making a mistake. of subtracting or adding. What the student did is they added 32. Let me just move the screen here. They added this. They added 32 to degrees Celsius. They added this 32 right here to degrees Celsius, and then they multiply by 1.8. I still remember that student made big mistake. So do this fast. I'm gonna put this in parentheses so that you do that fast, and then you add 32. 32. The opposite of this, that means to change the degrees Fahrenheit to degrees Celsius, that means you need degrees Celsius is given by degrees Fahrenheit minus 32 minus 32 over what? Over 1.8 over 1.8. These are the equation you should be able to manipulate to change from degrees Fahrenheit to degrees Celsius. This equation is not, if I want to change these to Kelvin, like that, there is no equation you can plug in. You got to change first of all to degrees Celsius, and then you go back to Kelvin. So if you want to change back to Kelvin again, you're gonna come back the same way, change to degrees Celsius, and then from there you can go back to degrees Fahrenheit. What I mean here is there is no equation. There is no equation you can use to just plug in the values in such a way that you will only end with Kelvin. You got to change this to Kelvin degrees Celsius first, and then you go back to degrees to Kelvin. Go back to Kelvin. That's what you need to know as far as the temperatures are concerned. 1.8, this is what I had before here. This equation right here is what I have right here. Degrees Celsius is 32. You subtract 32 from degrees Fahrenheit over 1.8. I'm using this 5 over 9. Same thing. I like working with whole numbers. I don't like fraction. If you can handle fraction, that's fine. Till you're gonna get the same answer. Let's see an example here. How do we change? All right, we have been asked, a weather forecast predict the temperature will reach 31 degrees Celsius. What is the temperature in Kelvin? So that is easy. That means we can change Kelvin equals to degrees Celsius plus 273.15. So this is 31 plus 273.15. And we don't have degrees Celsius for that. So if I add 273.15 plus what? Plus 31, 304.15. And this is Kelvin. What I've added is just add 32. No, 273.15 to 32. This is what I was given. The other one is I want to change to Kelvin. That means degrees Celsius to degrees Fahrenheit. Degrees Fahrenheit is given by 1.8 times degrees Celsius plus 32. So I'm just gonna multiply these first. 1.8 times 31 before I add 32. Before I add 32. So 1.8 times, all right, 1.8 times 31 plus 32. This is 32 right here. And I have 80, what? 7.8. This is degrees Fahrenheit. Degrees Fahrenheit. So I've changed that. This is the equation. How will I know that? You should be able to have it in your fingertips right here. To rearrange. If you want to use 5 over 9, 9 over 5, that's fine. You'll still arrive at the same answer. The same answer. Any question on temperature conversion? Any question? If there's no question, let's look at the concept of density. Density is defined as concentration of mass, and we can determine the density using the equation density equals to mass over volume. You know this equation, all right? And density equals to mass over volume. It is a physical property we can use to define or describe an object. Units derived from mass and volume. You see the equation here, mass over volume. I've seen students making mistake wherever you are asked, you know, if you know one, or if you are given two, you should be able to calculate the third one. I've seen students making mistake of flipping the equation and say, all right, he's asking me density, let me say, I think volume over mass. No, you have to know your equations. I'll recommend this if this is your first time looking at this equation and you don't know what it is, use this illustration right here. I'm just gonna draw this and put something like a T here so that when I have density, this is mass, and then volume. So that if I'm looking for density here, it is mass over volume. If I'm looking for density here, it is mass over volume. If I'm looking for volume, it is mass over density. So you look at it. If you're looking for volume, mass over density. And if you are looking for mass, given what? Given the density and volume, this is multiplication. You multiply this. You multiply here. This is multiplication. You multiply that, but the rest you divide, all right? These are the units used to express densities of common substances. You see here the substance and the density expressed in grams per centimeter cubic. Sometimes it can be grams per ml like that. It's because 1 ml equals to 1 cubic centimeter, or 1 cc. It used to be cc. All right, I don't expect you to memorize all this. You will be given if need be. All right, you'll be given if need be. Just remember the 3 equations that this is 1 right here. 2 is mass is given by density times volume. And then the third one right here is volume equals to mass over density. Mass over density. There are 3 equations. You can generate from one. You may be only given this one, but you should be able to get the other one. You should be able to get the other one. Any question on density? I know it's easy. Given any problem, use your calculator. Make sure that you pay attention to the units given and be able to proceed with the calculation. Earlier on, I mentioned about the exact numbers and inexact numbers. First, when we say exact numbers, there are 2 types of exact numbers. One is the divination, and the other one is obtained from counting. Counting, if I say I have 85 students in my Chem1 class, how do I know that? Or how did I end up with 85? It's by counting. How many days in a week? You count days, there are 7 days. How many quarters are in $1? You have to count. Those are exact. 7 oranges All right, how did I end up with 7? It's by counting. Those numbers are exact. And then divination, what does divination means? Something which has been divined. This is a divination. For example, right here, 1 hour equals to 24. No, 1 day, I meant to say right here, 1 day equals to 24 hours. These are definition. 1 hour equals to 60 minutes. These are definition. These are exact. 1 inch is equals 2.54 centimeters. This is a definition. We can also say 1 kg equals to 1,000 grams. 1 liter equals to 1,000 ml. These are definition and they are exact. There are some numbers obtained from measurement, from measured values. They have some degree of uncertainty. They are inexact because they are measured, and quite often there are errors. Maybe the instrument is not calculated. How you read the meniscus on a graduated cylinder can affect your final value. Say they are not exact values. So all measurements have some degree of uncertainty. The last digit in a measurement has degree of inexactness or uncertainty. Uncertainty is part of the measurement, and it is used in counting the significant figures. This uncertainty arises from either the person taking the measurement, or it could be from the instrument or the device being used. It can cause some degree of uncertainty. So don't think that wherever you measure something in the lab and the scale is reading 3.0000 gram, and then you're like, oh, I got the exact. No, still there's some degree of uncertainty, and you will see something like that, plus or minus. That means you can either add or subtract maybe 0.1 grams to give you a sense of what uncertainty is. All measurements have some degree of inaccuracy or uncertainty. In other words, this statement means, all right, in other words, this statement means no instrument will ever give you exact measurement because of the degree of uncertainty. And I have that as not inexact. Here is an illustration on temperature measurement. The last digit is always has some degree of uncertainty. It is just an estimate. We don't know where it lies here. We know the temperature lies from between 25 and 30, but here is just an estimate. We can say 27. There's some degree of uncertainty. Now, with respect to measurement, there are two terms here which you need to differentiate. With respect to measurement in the lab, there is the term accuracy and precision. Precision is a measure of how close individual measurement to one another, all right? How precise or how close to one another. It may not be accurate. For example, let me give you what accuracy means right here. If we know this is a true value, 1 inch equals to 2.5, what 2.5 for this is a definition. It's a definition, and this is centimeter. This is a definition right here. Suppose somebody measures, try to do some calculation, and every time he ended up with 1 inch. This is trial 1 inch equals to 1 inch equals to say 2.7 to 1 inch equals to 2.70. 1 inch equals to 2.71. If you look at this measurement right here, they are close to one another. We say they are precise. They are close to one another, but none of them is accurate. This is the literature file. But it is way off from the true file, even though they are close to one another, say that they are precise, how close to one another. Whereas accuracy defines how close individual to the correct. So if I do 3 times 1 inch equals to 2.54, 1 inch equals to 2.54, 1 inch equals to 2.54. 3 times, we say that they are exact. You know, refers to how closely individual measurement to the true value. You say, true value is what is given, the literature value. This is our literature. So wherever you are down the line, if you take organic or whatever you are writing your, report or conclusion, or somebody is asking you, can you explain your data? You can say, all right, from my calculation, I see my measurements are precise, but not accurate. That means nowhere close to the literature. It's okay to say that none of them is precise, none of them is accurate. All right, it can be a lose-lose situation. It's not non-precise, non-accurate. There's some illustration out there in online, talking about accuracy and precision. You may want to try and see what those mean. Somebody is using a dot here. If you look at this, if the eye pull right here, this is what the player is targeting. Good precision, good accuracy. Everything is in the eye right here, 3 of them. But poor accuracy. Accuracy is when they have everything right here, but all of them, they are at the top right here. We say that this is good precision. It's close to one another, but not really. But here is a lose-lose situation, poor accuracy and precise. You may be given in an exam or a question that a student A measured 3 times the mass of a penny, all right? Mass of a penny, and these are the values. And then student B weighed the same thing, and these are the values. Which student was precise, all right? Or what can you conclude about their measurement? It has to do with how you understand those 2 terms, precision and accuracy. Precision and accuracy. I'm a visual learner. If I look at the diagram given here, I can differentiate between precision and accuracy. Those are the terms you will, it sounds that you understand a lot. If you explain to your future instructors in the lab or wherever, like, precise and, know how to use, that you have learned what precision is with respect to accuracy. Let's look at real quick significant figures. We have about 29 minutes. Significant figures. When we say significant figures are important figures or digits. Sometimes we call it digit, used to express a measurement. Important, you are significant. Who is you are significant? Somebody who is important to you. Significant digits are used to express measurement, and reason this concept is introduced in chapter 1 is for you to learn how you will record your measurement in the lab. At some point, you will multiply numbers, you will add numbers, and does not mean everything you see on the screen on your calculator is correct. We're gonna learn how to express the final answer with the correct number of significant figures without writing everything. And first, let's learn the rules of significant digits. So, there are rules for counting significant digits. I know you know the concept of rounding off. This is coming in because you will multiply numbers, you will divide numbers, you will square numbers, all right? And you should be able to express your number with the correct number of significant digits. There are rules used to express significant digits, all non-zero digits to count. Let me give you an example here. 1, 8, 7, 7, 9. I'm just picking up a number right there, okay? I'm just picking up a number right here. This is a number all non-zero. They are all non-zeros. You can't counting significant digits from left to right, going from here, that this is 1, 2, 3, 4. 1, 2, 3, 4. So this has 4 significant digits, significant figures. You can say significant figures right there. All non-zero do count as significant digit. The catch is when you have zero. Zero is, all right, zero is how you have to be careful. Sometimes it counts, sometimes it doesn't count. Zeros between non-zero digits do count. For example, here 1 or 2, 0 between non-zero digits are significant. So this one has 3 significant figures like that. 3 significant figures. If I have 1, 2, like that, this one has 1, 2, 3, 4. This one has 4 significant digits. Zeros in between non-zero digits do count. Now, suppose now we call this leading zero. Suppose we have a number such as this, 0.0018, like that. Zeros at the beginning of a number are just placeholders. They are never. So how will I do that? Cancel. This is how you'll start counting significant. I'm just gonna start counting from here, like that. And this is 1, 2. This is 2 significant digits. 2 significant digits. All right. 2 significant digits. Zeros at the end, it must have a decimal point. Otherwise, they may not count as significant digits. 100 like that, should have a place of decimal to count. Zeros at the end of a number if it contains a decimal. If not, they don't count. So this one has 3 because of place of decimal. When zeros at the end, you have to use scientific notation to indicate that, all right? Use scientific notation. For example, here, this has 3 significant digits. Anything on this side of the multiplication sign, when a number is expressed in scientific notation, do count as a significant figure. Here is 1.030, 4 significant digits, 1.0300, 5 significant digits. What we are counting is anything on the left of multiplication sign do count as a significant. So what you want to do is, in order to avoid this, you can use scientific notation to express your final answer. What is the number of significant digits we have here in A? This has, how many significant digits does A has? Somebody somewhere there? Somebody somewhere there? No. 4, thank you, yes, Melly, thank you for Tierra, thank you. Queens, Cook, if you look at Y in A, zeros at the end do count as significant. For example, here 0.100, this has 3 significant digits. Anything after the decimal point here do count as a significant. So this one has 4, 1, 2, 3, 4. B here is 1, 2, 3, 4, 5. So here B has 5. 0. This is not placeholder. We call this these are not leading zeros. All right. C here is 1, 2, 3, 4, 5, 6. Z has 6 significant digits. The only thing here is understanding the rules, no calculation. Just given this, what are the rules? If I were you, I look at the relevant section in the chapter, look at the end of chapter problems, practice with the online, study modules, please do the homework on that. It is just easy. Once you nail it down, it's not calculation, all right? So I'm gonna ask you a question on how many significant digits are in this number, and then you pick up the answer, all right? Let's see significant figures and calculation. It's almost like the last concept we're gonna look at. A is, somebody's asking A, is A 4? Yes, A is 4, right here. 1, 2, 3, 4. Yes, Christian, 4. You're correct. Any other question before we look at the calculation? So I want to you to go to the relevant chapter and look at the calculation, significant figures. We will not do crazy calculation, just like in analytical upper level chemistry course where they look at high-powered calculation with respect to significant figures. But ours, I want to draw a parallel between two types of rules, laws. And this is a law for addition and subtraction. There is a law for multiplication and division. You see how I'm drawing a parallel? These are the calculation you will look at or will encounter. You may want to rephrase what I'm just putting across. Here you look at the decimal what? Decimal point. You look at the decimal point. Here you look at the, I'm gonna put a star. We look at the least, I mean to say least, figures, least significant figures. In calculations, you will do some calculation down the line using a calculator. A lot of numbers will just fly on the screen. It does not mean that whatever you have in there is more precise or you should express that. You should round off your number to the correct number of significant figures. Somebody is asking, what is the significant figures for B and C? Let's see if I think I have that. Let me see if I have that. P is 5. I think that is where it is. Let's see this one. P, 1, 2, 3, 4, 5. That is why I have 5 right here. And C is 6. 1, right? You count it here. 1, 2, 3, 4, 5, 6. That's why I guess I put 6. I could have put 6 right here. That's what it is. Thank you, Tiara. Thank you. So I was just explaining the significant figures and calculation that everything you see on your screen is not correct. I know one of the multiple choice you will encounter for multiple choice exam is whatever you see on the screen. It's not, does not mean that it's correct. No, there's a procedure you should follow, or there's a law, there is a rule you should follow, rule of thumb for addition and subtraction. Look at what I've underlined. Subtraction and addition is right here. You look at the least places of decimal. If I have, for example, 1 or 10.1 plus 2.34, for example, 5. This one has one place of decimal. This one has 3 places of decimal. So your final answer, if I add this will be 12.445. Your calculator will give you something like that. It does not mean it's correct. You look at the least place of decimal. So if I do that, this will be my last. My final answer, I should have 1 place of decimal because of the least. You see what is written here is least, and there is the rounding off. Look at this. I know you covered the concept of rounding off. If it is equal to or greater than 5, you increase this number by 1. If this was 5 or greater than 5, we'll increase this by 1. So this will be 12 point. This will be 12.12. This will be 12.4. All right. This is 12.4 because of one place of decimal. If the other one didn't have, if this one had no place of decimal, my final answer will have no place of decimal. If the first number here didn't have any place of decimal, it's just gonna be 12. You do the same thing for subtraction. So subtraction and addition goes hand in hand. Goes hand in hand. So that's how you do, you carry calculation with significant figures. For multiplication, you look at the few or least. You see what I've written here, like least, what I've written here is least significant digits. Multiplication and division right here, you look at the fewer number of significant digits. If I have, for example, 2.3 times, let's say even right here, 2.3 centimeters square, or no, centimeters times 1.58 centimeters. This one right here, if you look at the significant digits, this has 2, this has 3. So the final answer should have 3 significant digits. Let's multiply that, okay? If I multiply that, 2.3 times 1.58, I just made up those numbers. I see this 3 point right here. My calculator is giving me 3.6, 3, 4. And remember, you multiply units, so this will be centimeters square. It doesn't mean it is correct. No, it's not correct. It's not correct. The rule for significant figure, it should be the number of significant figures, the one with the fewest, control how many significant figures will have. And there is the rounding off. Answers are rounded off to the same number of significant figures as the measurement with the fewest or the least. Fewest or the least is the same thing. I like to go with the least. That's over the years, I've just configured my mind that it's the least. So here, in my example, or in our example, 2.3 has the least or few significant. 1.58 just the greatest number of significant figures. So we go with the least. And what we will do here is, we'll stop right there. And this one is less than. 3 is less than, right here, it is less than 5. So we will round off to 2 significant digits. And the final answer should be right here. The other one didn't have units, so this will be 3.6. This is centimeters square. This is centimeters square. That's what you do for division as well. That's what you will do for division. So pay attention to rules for addition, subtraction, multiplication, and division. I've seen students like, switching the rules, like they are applying for multiplication and division on addition and subtraction and vice versa. You could ask me, suppose you have 3, 3. If it is 3, 3, it doesn't really matter. No one, it's it's the same thing. If this one had 3, for example, if this had 3 significant figures, this one had 3 significant figures, and then we'll just round off our final answer to 3 significant figures, 3 significant figures. So you drop the rest, all right? You got to know how to drop the rest. Let's see an example here. If you have your calculator, all right? If you have your calculator, if you have your calculator, if I look at this, 14.3505 plus 2, all right, I mean 2.65. My calculator is giving me 17.0005. If I look at the places of decimal, it should have 2 places of decimal. These fall under addition and subtraction. So this has 2 places of decimal. This has 1, 2, 3, 4. Not significant. I've seen students counting significant figures. You know, it's not. Places of decimal. 1, 2, 3, 4. 4 places of decimal. 1, 2, 2 places of decimal. So my final answer should have 2 places of decimal right here. I'm gonna stop right here. And then look at this number right there. And simply this will be, all right, this will be 17.00. This one is just, I dropped the non-significant. You don't go down and pour it and then bring it over here. No, you don't do that. So this is what you need to do for that. A, this is A, and B right here. This is division. And if I plug in my calculator, 0.05, 88 divided by 0.6, 7. And I have on my screen 8.08, 6, 85, 853, 766, a lot of numbers, you know, a long number. If I look at this number here, this is division. So we look at which one has the least number of significant figures. I look here, I cancel this. This doesn't count. These are leading zeros. 1, 2, 3. The top one has 3 significant digits, and the lower one has 1, 2, 3. So both of them have 3 significant digits, so it doesn't really matter. I should round off these to 3 significant digits by just canceling the leading zeros, and I count 1, 2, 3. I'm gonna stop right there, and there was a 5 there, so it's 0.0869. That is the correct answer, going by the significant digits. Going by the significant digits. That marks the end of section 1.6. I don't want to start off section 1.7. We'll finish section 1.7 and move on to chapter 2 next week, Tuesday. Please continue reading on dimensional analysis, and we will meet again same time on Tuesday. Please continue working on the online assignment. Please continue working on the online assignment. I made the changes on the first introductory. Otherwise, thank you for tuning in today. You don't have to, it's gonna capture, you don't have to say yeah, yes today. Every time you log in, I will see that you log in or who was in the conference. In fact, I see how long you stay on the conference. Yesterday, some students stayed for a minute. I said, wait a minute, maybe they know what's going on. But thank you. Be safe. See you next week. I appreciate your time tuning in. If you have anything, please email me and I'll get back with you within 24 hours. The class is dismissed. See you same time. Appreciate it. Bye.